Good morning. Today we're going to have a review on classifying matter. We have our retest on Wednesday, tomorrow, and today we're going to just go review this again because I want to clear up a few misconceptions and a few things that I saw people miss most often on the first go round at the classifying matter test. So just to remind everybody that matter is all the stuff in the universe that has mass and volume. So anything that we can weigh and measure. Things that are not matter would be things like electricity, energy, light. And although we can measure them in amounts, they do not have mass and volume. So I'm going to slide this up a little bit out of the way. And we're going to talk a little bit today about matter. So when we talk about matter, we want to take all the stuff in the universe and we want to separate it into different types so that when we are looking to make new things, build new things, we know what we're dealing with. And one of the things that we do first is we try to figure out what's pure. What is only made out of one types of substance? So when we classify matter, two of the ways that we classify matter are whether or not they are a pure element or if they are a pure compound. So they're either one or the other if they are pure. And a pure element contains only one element from the periodic table. A pure compound will have two or more chemically attached different elements. They'll make one kind of compound, but it'll be made out of two different elements. Now, when we talk about a pure element, an example of a pure element would be carbon. Carbon is found on the periodic table. And when you take your quiz, sort of a hint that we're talking about an element is that I will give you the element symbol from the periodic table in parentheses. You've seen this before as we've worked on our chemistry unit. Okay, so what does that look like? Well, when we do our particle diagrams, you will see that when we have carbon in my little container here, let me adjust this a little bit better. When we have our container of carbon, what you will see is every single element atom is exactly the same. There is only one kind of element in my container. So that's how I know that it's pure. There is one element from the periodic table in my sample. So when I'm looking at all of the matter in the universe and I want to know if I just want to make this as pure as it can be, just one element from the periodic table, this is how I would notate it. Now, there are a few atoms on the periodic table that we've talked about previously that don't travel alone, and one of those is oxygen. Oxygen always has to be bound to another element. So when you see oxygen in a sample, you will see that there will be two of them attached to each other. And sometimes people confuse that as a compound. But the thing you need to notice is that all of the individual circles here, the individual atoms in our sample, are identical. Just because they're attached to each other doesn't make it a compound. It makes it a pure element. There is only one type of element, oxygen, in this container, and its chemical formula is O2, but it is one type of element, so it is a pure element. Our next type of pure sample is a pure compound. So not quite as pure as a pure element, but still pure, is to have two or more different kind of elements that we have chemically bound together to make only one kind of compound. So my example here is carbon dioxide. In my little container that I drew here, I have carbon dioxide whose formula is CO2. So the C in blue is to show you the blue atoms here. That's the carbon. And then for every one carbon, we have twice as much oxygen. So here are your two red colored oxygen models for my example here. And every single one of these compounds, here's a compound, here's a compound, here's a compound, here's a compound, are all the same. They are carbon dioxide. There are no other types of compounds inside of our sample. Okay, now some other things that we do is we may have multiples of a much more complicated compound. So for example, I could do glucose, C6H12O6, and I could have nothing but these very complicated molecules in my compound. And you see this when you look at something like sugar. This was from our lab, and we had nothing but C6H12O6 pure sugar in our container in this bag. And that was one of the samples from our lab. So that was an example of a pure compound. Pure oxygen, you'll find in the bottle of oxygen that maybe you might see in an older relative's house if they are using oxygen. Pure carbon is what you will find in a diamond, or sometimes in the tip of your pencil is made out of pure carbon. Okay, continuing on with the only one of four types of matter. So if something is not a pure compound, then, because remember, it's either a pure element or a pure compound, or our other choice, next choice, is a homogeneous mixture. In a homogeneous mixture, every drop looks identical, but there are several compounds in it. It is not a pure compound with just one kind of compound in it, like our sample of carbon dioxide here. In a pure compound, you would have evenly spaced out molecules in such a way that you could not pick apart where one part of the heterogeneous mixture started and where the next part ended. So, an example of that would be milk. I know a lot of people think that milk is one thing. Milk is not one thing. It looks like one thing. Every drop looks identical, which is what makes it a homogeneous mixture. The prefix homo in Latin means same, and all of this mixture looks the same. But milk, if you've ever really thought about it, I mean, milk is one of those foods that we talk about being highly nutritious. Milk is more than one thing. It has compounds of protein in it. It has compounds of water in it, compounds of glucose, compounds that contain vitamins, compounds that contain minerals. But these compounds are all broken up so small that every drop looks identical, even though there are several compounds in it. Now, our fourth choice, remember, there are one of four types of matter. You're either just an element, one kind of compound, which makes you a pure compound, or several kinds of compounds mixed together, but they're so small and they're mixed so well that every single drop looks the same, like milk, or you're a heterogeneous mixture. Let me move my mixtures over here. Or you're a heterogeneous mixture, which means that you could call different bits by their own name. As you look through them, you can clearly see there are several compounds in it. So here's my example of my compound, and I give the example of peanut butter. Peanut butter, like milk, has many compounds in it. We give it one name, peanut butter, but peanut butter actually has fats, protein, glucose in the form of carbs, vitamins, minerals. But peanut butter oftentimes is not a homogeneous mixture. In fact, if you look at this jar of peanut butter here, I don't know if you can see it, there's some oil at the top, and I've circled on here all of the things that let you know it is not homogeneous. It is heterogeneous. It's got fiber, it's got sugar, it's got calcium, it's got potassium, it's got fat. There's no way that this is a pure compound or a pure element. It's got too many kinds of things in here. Now, this can be tricky because the ingredients say just peanuts, but you have to think about, is peanut an element? Is there a chemical formula for peanut like there's a chemical formula for sugar? I think not, because you have so many different things in your heterogeneous mixture. Now, one of the things that seems to confuse people is when we start to talk about the examples. So I'm going to give you a few examples here one more time of the different types of either pure element, pure compound, homogeneous mixture, or heterogeneous mixture. You cannot be a little bit of one and a little bit of the other. You have to pick. And one of the things that I noticed on the original quiz that I gave was that people would say things like pure mixture or heterogeneous compound. Please do not mix up words from different columns. These go together. Pure an element, pure and compound, homogeneous and mixture, heterogeneous and mixture. You cannot mix back and forth between columns. So first up, here I have some, you've all seen this before. This is aluminum foil. Aluminum foil, perfect example of malleable, right? All of the atoms inside of this sample are just aluminum atoms. Al from the periodic table, that would be a pure element, one element from the periodic table. Our next example would be the sugar that I showed you earlier. Everything in here is C6H12O6. That's the formula for glucose, and that would be a pure compound. You have carbon, hydrogen, and oxygen all bound together, but there is only one kind of molecule, C6H12O6. And I guess you could call that glucose for short, really quick. But it's basically sugar, as we know. Sugar is a term that we use for a lot of different, very similar formulas. Sometimes it'll be C6H12O5, but they're very, very similar. They all are carbohydrates or sugars. Our next example of a homogeneous mixture where everything looks the same is my ketchup. Here I got a bottle of ketchup. Um, and every bit of this ketchup looks the same. I can't point to it and say, oh, I see something floating in here. It all looks like the same yummy stuff that makes my French fries taste awesome. Okay, next one, heterogeneous mixture. Heterogeneous mixture is where you can pick out different bits and you could name them. Like, for example, when I look at my salad dressing here, and again, here's a dead giveaway that this is some sort of mixture. Look at all these ingredients. Although peanut butter and milk only have one thing, when I start reading this label, I can see that there's sugars and sodium and fat and carbs. Not a lot of vitamins. Salad dressing's mostly fat. But when you look at it, I can see bits of herbs and spices, and I can see oil at the top, and I can see that this has clearly got different bits that I can pick out. Did give away that there's all different parts in here, and that's a heterogeneous mixture. Now, a little harder to see is this apple juice, and I don't know if you can see in the bottom here, but there's a layer here that is thicker. Like there's some pieces that have settled out into the bottom of this container. Anytime something says shake before serving or shake before using, that is a dead giveaway that you have a heterogeneous mixture. Now I want to show you one more homogeneous mixture because this is one of the trickiest examples in our quiz and in our lab, and that is water. So here I have a bottle of smart water, and it says something very interesting on the bottom. I don't know how well you can read this, but it says vapor distilled water and electrolytes for taste. Now, you may remember from our chemistry unit that anytime we add a positive or negative ion to something, that is an electrolyte. That's all an electrolyte is. That is our calcium ion, magnesium ion, potassium ion, all of those things. So if you look at the label here, and I'll read this to you, it says vapor distilled water, calcium chloride, magnesium chloride, potassium bichloride. All of these are added to make the water taste better. Water, when it's pure, does not taste very well at all. But what is distilled water? Distilled water is actually pure water, and you can buy it in the grocery store. It looks like this. And what they do is they boil the water and they catch the steam. When you boil the water, the steam that comes out of the pot is only H2O molecules. So this type of water, distilled water, would be a pure compound. In the container, there is only H2O molecules and nothing else. Nothing is added to this. And through the boiling and capturing the steam and cooling it back into liquid water, they managed to get only H2O molecules. Let me get my camera to focus back again. This smart water, they started out the same way. They captured all of the steam and then they said, okay, we're only going to put back in the things we think are going to taste the best. And they added some other types of salts to it, which makes it a homogeneous mixture because it has Every drop looks identical. I could scoop out teaspoon after teaspoon of this water, and every bit would look identical, but it has multiple compounds in it. It has sodium chloride and magnesium chloride and all of those things. Now, we're going to talk about one more thing. So let me get all this stuff out of the way. We are going to talk about ways to describe mixtures. Another mistake that I saw on the quizzes that people were just confused about was what to do with the words colloid, suspension, and solution. So, colloid, suspension, and solution are only ways to describe mixtures. We never use these for pure substances. And I know it's confusing because you have all of these um, advertisers who lie to you and call something pure. That's not a scientific term the way that they're using it. The word pure means only one kind of atom or one kind of molecule, like in our bag of sugar here, one chemical formula. Things like ketchup and salad dressing and peanut butter and juice, all of these things are not pure. They have many different substances inside of them. Uh, when we talk about mixtures, we are going to use some words to describe them because it's useful to us if we were going to make new substances. So, this is part of what happens in manufacturing and in product design. We need to know some things about them so we understand how to package them, we understand how to take care of them before we're going to use them in something else. So, our first one is the colloid. A colloid is something that is so thick, light would not pass through it. So, a lot of times when you see a colloid in the grocery store, they don't even bother to put it in this nice clear packaging because what's the point? You're not going to see anything in there that's going to be of interest to you. So they wouldn't go to the trouble of making all of this clear packaging. And a colloid, it's so thick or it's got so many particles in it, you can't see through it. Some common examples of colloids would be things like ketchup, peanut butter that is creamy and doesn't separate into an oil layer, and milk. Those are some really good examples of some things that are colloids. So colloid, things where light won't pass through. Okay, our next one is the suspension. The suspension has those words shake before using. I'm trying to see if they put it on here. I think here we go. Shake well and refrigerate after opening. The refrigerating is so it doesn't go spoil, but the shaking is because if you do not shake this, your first 25 servings of this is going to be pure oil with no flavor. And then at the bottom, you're going to kind of have some dry bits in here that are going to come out, and you're not going to have that nice slippery oiliness to get it to coat all the pieces of your salad. So this is a suspension. Suspension, like these pieces get suspended for a while when you shake it up. Same thing with this apple juice. I don't know if you can see some of the bits there in the bottom. If you don't shake this up, then the first few sips are going to be really thin. And then when you get to the bottom, you're going to get some thick bits. And to have a lot of them at once might not be very pleasant. So that is a suspension. And then here again, we have the peanut butter that's got sort of that oily layer at the top. Some people like to buy this because they don't add a lot of extra chemicals to it. They say, I'd rather stir it and not eat the chemicals than have the chemicals that they use to make it stay as a colloid. And then lastly, some solutions where light would pass through and you could, look, you can just about read through this bottle, right? So this is a great example of a solution. It stays mixed. You do not see a layer of the magnesium chloride and the sodium chloride in the bottom of the bottle. Other things that stay mixed would be when I brew a cup of tea. Generally, when I brew a cup of coffee, when I buy Gatorade in the bottle, I don't have to shake it in order to enjoy it. And I can see through those things, maybe not as well as you can with water, but in generally the light's going to pass through. And in some of the examples in the test and in the lab, I held things up to the light so you could see, was there any light passing through that would make it a solution, or was there no light passing through? That would make it, or nearly no light, that would make it a colloid. And then again, a suspension could have some light that passes through, but the fact that you have to shake it basically says it can't be a colloid and it can't be a solution. If you have to shake it, it's automatically a suspension. Do not worry if it's a colloid or a solution. If you've got to shake it to enjoy it, it is a suspension. If you don't have to shake it to enjoy it, then you have to decide, does light pass through it or does it look clear-ish? Maybe it's got a light amount of color to it. Hopefully this has cleared up some of your questions about matter. And remember that there are 4 types that we use to describe all of the stuff in the universe. And then these words are used to describe just the mixtures, to be a little bit more specific, because most of the things in the universe are a mixture of many things, especially the things that we can buy in the store. Okay, I will have more examples available for you today in class. If you were there and you then got to watch this video, you got to see those. If you were not there, please go and use that quiz. Either way, please go and use the quizzes for some practice, and make sure that you've completed that lab before we take the retest tomorrow. And then we're moving on to nuclear chemistry, which we had started before all of this break in our in-person learning for virtual learning. Thank you very much, guys. You're awesome. I'm so glad you're here and that you are making a great decision to keep up on your schoolwork. You're a rock star, and I'll see you in class. Bye.